So I was going to show some about nonlinear solvers. I mean, I just want to show that you can do this with nonlinear solvers as an example. And I think it'll eventually affect PyLith because we are doing nonlinear. I mean, for instance, like we don't concentrate on it, but the nonlinear rheologies are going to start being, important, especially if you really want to figure out where they matter. And so let me show you a simple system where I do the same thing, where I, make progress. So the very simplest system I could think of to do this was the driven cavity system. It's like Stokes with temperature. And so you have the controlling numbers, it's got a Rayleigh number because it's got a Prandtl number and a Grashof number. And if I fix Prandtl, then the Grashof number is the Rayleigh number, okay? So I'm just heating a box from the bottom and banging on the top, right? And so it's not sophisticated. But what the heating does is kind of initiate convective stuff. And the banging on the top means I got to take into account I'm shearing it. So it means I got to take into account the stress behavior there. And you can get very thin structures. And so here's a very small, this is a 16 by 16 grid and a Rayleigh number of 100, and you say, no problem, right? And then I can raise the Rayleigh number to 10,000, still no problem. 100,000, okay, stuff goes wrong. And this is the same kind of thing that we were doing in the linear case, only it's nonlinear, it's that the nonlinear solve didn't work, okay? Now, nonlinear solves are, for the most part, not always, made up of linear solves. So if you do Newton's method solves a linear problem each time and then takes a step. So it's a diverged nonlinear solve. So what we should have started out with, as I said, is always hit it with a hammer. So I'll just do LU factorization. Now, no problem with the linear solve, but you can see that problem was just papering over the underlying problem, which is the nonlinear solve was getting hard. And when the nonlinear solve gets hard, the linear solve gets hard too. And so I just don't converge at all for this Rayleigh number. So there's a lot of things you can do, and there's a really excellent web page about all the possible things you could do on this website called Stack Exchange SciComp, so Scientific Computing Stack Exchange. If you have solver problems, that is a good place to go, because people will answer your stuff. And you can check a whole bunch of things, which I won't go over in too much detail unless people ask. But in the same way that a linear solver can be composed with another nonlinear solver, and you call it preconditioning, a nonlinear solver can be composed with another nonlinear solver, and you call it preconditioning. That's just the message. And they have different strengths and weaknesses. That's why you do it. So I don't want to talk about that. Let's just do the example. So here I'm going to say, let's back off. Let's try to find exactly where things start to go south, right? So at a Grashof number of about 50,000, I'm sort of making it. I get pretty far, and then Newton sort of peters out. So what if I say, oh, I don't do Newton because Newton's obviously not working. What if I do Newton on a series of smaller problems? And so I'm going to solve Newton on the coarse problem and then use that and just refine a little bit and use that, refine a little bit. We can call this, this is called in numerics FAS, the full approximation scheme, or nonlinear multigrid. It's just solving a nonlinear thing on a sequence of grids. And here, it looks like it's going even farther and it's going to work, and then it's just, it craps out. So what's going on? It says diverged inner. So when you have solver problems, there is always more monitoring that you can turn on to see what's happening. So here, let's say, what is the reason for convergence or non-convergence at the coarse level? So what it says, we say, okay, I'm doing pretty well, and then it tells me, oh, my line search for Newton didn't work on the coarsest level. So you say, okay, well, get rid of it. Get rid of the line search. And so, okay, so now the nonlinear solve is really working on the coarse level. I'm still not converging. It's pretty disheartening. But I'm getting farther. And you say, okay, well, what's going on? Well, I'm using a pretty weak upper level solver. I'm just doing this one equation at a time, like solve this one and then solve this one and solve this one. What if I did something stronger, like at every level I'll do Newton? Well, okay, I won't do that yet. What if I, instead of doing that thing alone, what if I used a preconditioner, which is say, I will get the answer from the multi-level nonlinear solver, and then once I've got it, I'll take one step of steepest descent. Now, steepest descent is really weak and very slow, but very robust. So it can take tens of thousands of iterates, but it always makes a little bit of progress, or generally makes a little bit of progress. So if I combine the two, the very slow but robust thing with the fast but non-robust thing, and I can do that just by changing, I say I have a nonlinear preconditioner for the steepest descent, I actually get convergence. And the cost is nothing. It doesn't cost anything extra, basically. It's just the right combination. And so it takes 45 iterates to converge. Not bad. What if I use something better than steepest descent? What if I used nonlinear GMRes? Now it looks a lot like what we're doing in the linear case. I'm using a Krylov method, only it's a nonlinear Krylov method. And I'm using a multi-level method, nonlinear multigrid instead of multigrid. So it's like, it's exactly like what we're doing for PyLith, which I think is why it will work for PyLith. And I can have the number of iterates almost, so 45 to 29. And then what if I did the sledgehammer again? So I do something expensive. I do Newton on every level instead of this easy one equation at a time. Then I can take 5 iterates again. And the thing works. And this is very, very robust, and I can do very high relay numbers. You can do other things. So nonlinear, there's a wider space of nonlinear things. So I can take the Newton that failed, and I could take the multi-level thing that failed, and I can actually stick them together, and together they work pretty well, and they succeed. And there's not good theory for this. That's the unfortunate thing. The linear stuff all has good theoretical underpinnings. This doesn't. But this works, yes. Additive optimal. So I take alpha times one of the solutions plus 1 minus alpha times the other solution, and I do a simple bisection to figure an alpha, and it's amazing. And this is stuff that they were doing in the 60s when they had very little memory, right? So they're like, how can I reuse these solutions and do better? And it works. And if you do multiplicative combination instead, where solve one, use it as the input, solve the other, and then alternate, that's even better. That goes 500. So there are a lot of ways to combine these things. Although these are two very expensive solvers, and before I was combining one expensive, one very cheap. So you have to be more careful with doing that. But, I can tabulate everything, and you can see that, simple combinations like plus and times, additive and multiplicative, they work pretty well. But even better are these preconditioning combinations that I showed you. And I don't want to go in too far into what that is unless people are interested, because it's algebraically more complex. But it works very well. And so my feeling is what we could do is use these kind of solvers for PyLith when you're using nonlinear rheologies or nonlinear feedback. Like say you had a poroelastic problem and you had nonlinear coupling like through the coefficients in one equation from the output of another equation, stuff like that. Then these are the kinds of things that will work. And in fact, one of the things that I've run them on that works pretty well is magma dynamics simulation. And all magma dynamics is it's two-phase porous flow where you have two viscous materials, and one is the aggregate and one is a fluid inside it, and the aggregate is allowed to deform. And so this would look a lot like a poroelastic simulation, something like PyLith. And the permeability is usually a nonlinear function of the porosity. And so you get highly nonlinear solutions there. And I know it would be similar here. And this is all detailed in this paper that we wrote, and we show a lot of examples. We actually show a nice example of large deformation elasticity, which I didn't go over, but I guess I could have gone over. And we do a bar that gets close to snap through. And that also, if you're doing a large deformation problem, you need nonlinear solvers, and it can get hard if you are close to one of these bifurcation points. The Jacobian gets singular looking. And then you can, of course, mail us for other solver-related things. Okay. So there's specific solver questions of stuff you want me to go over, stuff that you don't understand, or has anyone heard of a solver that they think is cool, but I did not talk about it all? So it's my chance to disparage it. Okay, so hopefully it's clear how you should go about starting out a simulation, so use a sledgehammer solver, and then scaling up a simulation, so consider the parts and start backing off individually while checking your solution. And then if you really want to get very large, I would say you can talk to us, and we've run larger things, so we can give you advice. And there's actually a large section in the paper that we wrote in JGR about PyLith about reading the log summary times and interpreting what they mean in terms of your machine architecture and how the convergence is going and stuff like that.
Well, Matt, talking about iterates,
yeah.
What probably really matters to you is runtime. And so, well, Matt may want 10 iterates sometimes, like in our examples, we may do 200 iterates, but it takes, 2 seconds for a bid to make 10 seconds.
That's right. And
but
so, as you scale up, so the reason that it's complex as you scale up is that some of these things increase at different rates. If everything increased linearly with problem size, then we would all be done. We would know by running a small problem how a big problem would behave. But a lot of these things are nonlinear functions of the problem size. So there's crossover points and all this stuff where you want to change what you're doing. So you really have to reevaluate at each sort of power of 10 up of problem sizing.